Obviously, a simulator is important for this whole process. What are the things that you should be looking for? As already mentioned, right, the quality of your simulation will only be as good as the accuracy of your simulator. If it's not able to properly model all of the processes at play, then you're going to get wrong answers. And the accuracy that you want to be focusing on, I mean, in general, has to be accurately modeling what the quantum physics is happening at a low level. It needs to be able to properly account for various sources of uncertainty and error and quantum noise. As we've been talking about, the noise and loss experienced by qubits is very, very important to understanding if your design will actually work. So being able to properly model these is very, very important. And also being able to have a simulation in time, but which you have very precise timing resolution on, so that you can say, did these qubits arrive at the same time within a picosecond or not? These kinds of things. Assuming your accuracy for your simulator is all good, what's the next thing you need? If you want to be able to efficiently design a network, it means being able to try different things quickly and iterate quickly. And so because of this, it's really important to have your simulator be flexible and modular in how you go about defining components and protocols, and how you go about putting them together. And you should picture a bunch of pieces that a simulator can give you, and you're the one who can go about and put them together in various ways. And it should be easy to take out one here, put in something else, tweak this, and in general be able to iterate on different designs. Another consideration is, of course, as much as possible, we would like our simulator to be scalable to large networks, to large quantum systems. And of course, there are fundamental limits to how large of a quantum system we can represent efficiently on a laptop, right? But there are ways that you can sort of take shortcuts or be smart about how you interact systems or how you represent quantum states. And so, as much as possible, making sure that your simulator is scalable from very small photonic level physics to large scale networks. Because we want this scalability, but we also want to be able to look at very precise physical systems at a very low level of detail. We need flexibility in the level of abstraction in which our simulator can actually operate. So what I mean by that is, let's imagine that you are just starting out and you want to design a link between two nodes, and you know that these nodes should have certain kinds of of sources and timing and detectors and beam splitters and all the optical stuff that you need, and you want to go about and make sure that this whole design actually works for generating entanglement between those nodes, right? This is kind of like a low level, can you get your elementary entanglement generation working properly? And so for this case, we need to be able to simulate very accurately all the quantum physics and the optics. We need detailed hardware descriptions, all that stuff, right? On the opposite end, we want to be able to have many node systems distributed across large scales, and be able to study the behavior of that large system and how protocols on the system will actually behave. In the middle, right, we have this kind of intermediate section where we have a few nodes that have some devices attached, and we don't necessarily need to know all the specifics about how each entanglement is formed, but we do want to know, once it is formed, how are we going to use it, and can we use it effectively, right? And so there's various levels of abstraction that one has to go through when going from a first experiment to a wide scale network. And I'll mention that in terms of the open source quantum network simulators that are currently available, they tend to focus more on these last two sections, right? Whereas for the purpose of early testbed development, what you actually want is the ability to really go deep into the quantum physics and optics and make sure that your devices that are connected will actually function like you want them to. And so understanding that what you need for your level of development is important. So it depends. If you are absolutely sure that if you're absolutely sure that each individual piece of your network and each individual link and each individual subsystem will work as you expect, then you probably can get away with that, right? If you don't need to know how each entanglement is being generated, you just need to know, say, how good it is or how long will it take to make. You don't have to go through all of the details of that if you don't need to, if you already know how good it's going to be, right? Similarly, if you have sort of a larger system that you have already tested extensively, know how it's going to function, you can take that information, put it into a simulation, and sort of have a higher level abstraction simulation where all the details of how the hardware works, say, is just ignored. We know how well it does what it does and what it does, so we can just use that. If you are at an earlier at a stage where you don't know yet if all of those things will work as expected, then you have to go through a more physical quantum-based calculation. So it really depends on sort of how sure you are that you understand how that lower level of abstraction actually works. Yeah.
Okay. So it sounds like it's highly recommended to simulate across all levels if possible.
It depends how sure you are. If you already have, or you have already done experiments that your system will work, then you're good to go. But yeah, if you're starting out, then you should start out at that lower level for sure.